Hey friends, here we are in our next lesson. This one is about the laws of logarithms and solving equations using them. When we're going to use these, if you remember last lesson, what we were doing is we were solving equations that looked like this. And we were able to do that by making the bases the same. Logarithms are going to help us when we can't make these bases the same. So that's what I want you thinking about today. Now, before we begin today's lesson, I'm actually going to go and I'm going to talk about a little bit about the history of logarithms first. Now, I know as soon as I say that, I'm like, I'm going to teach you some history of math, and I can feel the collective moan over the internet here going, oh, really? Yeah, really. This is actually going to help you. So I have another video all about this, but I'm going to give you a short, brief summary of it here. What I need you to remember is that logarithms are inverses of exponentials, meaning they undo our exponent laws. Okay, how does this work? Well, it works like this, and this is the story, is that there was this French mathematician by the name of Napier. He was actually working with a Swiss guy, but I can't remember his name. And the scientists were working with a bunch of numbers. I believe they were measuring in radians the heights of stars on the horizon or how far they were moving. It doesn't matter. Okay? But they were getting these long decimally numbers. And I don't remember this story, but for some reason they had to multiply these things together without a calculator. This is like the 15 or 1600s. Can you imagine doing that without a calculator? You're going to screw up. So what Napier and this other mathematician figure out is they say, oh, I can't multiply these together. Me trying to multiply these things together right here is awful. Multiplication, bad. But they have this brilliant idea of saying, but I could add these things together very easily. I could have added those things together in grade school really easily. So what they really end up doing is their goal, and it takes them a while, but their goal is they kind of make a cheat chart, like a life hack. And they figure out how to turn multiplication into addition. I'm going to say that again. This is the most important part. Their goal was to turn multiplication into addition. How did they do that? Pretty nifty. What they did was they invented something or discovered something known as a logarithm. So I'm going to show you how this works. This is the really important part here. So I'm just going to pick a number, let's say 8. Well, I know 8 is really 2 times 2 times 2. Okay, I know I can multiply those together easily. It's 8. I know you can do that too, but just play along. Let's pretend this is back when they were trying to work on this, and his goal was to turn multiplication into addition. Here's how he did it. They did it. They invented a function or discovered a function called a logarithm. Now, a logarithm, when you use this button in your calculator is performing a massive calculation. Don't worry about that. It's the same as when you hit square or square root. You don't know what your calculator is doing. You're trusting it though. So they say, look, we're going to turn multiplication into addition. That's the key takeaway from my little history lesson. So if I want to turn multiplication into addition, and I can do that using logarithms. Okay, right there is our very first law, right here. That log base A of B times Z is really the same as saying log base A of B plus log base A of C. So that was their first goal. Multiplication turns into addition. They did that by using a logarithm. Now, guess what? Once you know that, the other important laws fall together. What do you think? If multiplication turns into addition, what do you think division would turn into? Well, if multiplication turns into addition, guess what? Division is going to turn into subtraction. Now, I'm not proving these to you. It's just a little lesson to help you understand. Okay, these are definitely not proofs. All right. Now, the law that we're going to need to use the most is actually this bottom one here called the power law. So this one here, I'm going to show you where this comes from. So I'm going to go back up to here, and I'm going to go back to right here. And it all goes back to their goal of turning multiplication into addition. So log 2 times 2 times 2 is equal to log 2 plus log 2 plus log 2. Come on, let's keep working with this. I know there's a better way to write this. 2 times 2 times 2 is really 2 cubed. Agreed? Hope you agree. And on the right-hand side here, I know there's a better way to write this. Log 2 plus log 2 plus log 2. Like if that's at x plus x plus x, you would say that's 3x. Well, guess what? Log 2 plus log 2 plus log 2 is 3 log 2. Here it is. What I really want you to notice is this. Look at your exponent here. Your exponent can become your coefficient. There it is. There's our final and probably most important law for today. That down here. My exponent or my power can become my coefficient. There it is. See, that wasn't a bad history lesson. All again, I really want you to remember is Napier's goal was to turn multiplication into addition. And everything comes from there. If multiplication turns into addition, division turns into subtraction, and from the multiplication law, we see where the power law comes from. Okay? Again, not a true proof or anything, but it's going to just help us get through. These are all on our formula sheet. No need to memorize anything. Please, when you're doing or working with logarithms, keep your formula sheet in front of you. Okay, I cannot stress that enough. Keep this formula sheet in front of you. Okay, how does this help us? Well, it says solve the following algebraically. So the first thing I look at is I say, can I make the bases the same? Not that I'm aware of. Okay, so what I'm going to do then is so step one, we try to make the bases the same. If I can't, what I'm going to do is I'm going to take the logarithm of both sides. Okay, remember when we were little guys and we were in elementary school, and your teacher always said, what I do to one side, I do to the other. Because remember, we're not changing what this thing's equal to, we're changing how it looks. Okay, so I take the log of both sides. Now I'm going to use my power law. So that exponent of y can become my coefficient right here. That was really important. And now to isolate for y, I'm going to divide both sides by log 10. Log 10 is a number. I don't know what it is, but I know it's a number. Okay, I can go and put that in my calculator. Log 81 divided by log 10, and you're going to get a value of approximately 1.91. That's it. Let's try this again. So, next question. First thing I try is say to myself, can I make the bases the same? Answer is no, so I use a logarithm. Take the log of both sides. Take the log of both sides. Then, what I say is, My exponent can become my coefficient right there. And now divide both sides by log 5. And that can be put in my calculator. And we again get an approximate value of 1.3-ish, 1.32 we'll say. Okay, let's keep going. That's it, guys. Once you got this step, you've pretty much got it. C. Can I make 6 and 12 have the same base? Sir, no, sir. So I take the log of both sides. My exponent becomes my coefficient. I said it and I didn't write it. I got to go write that log there. Sorry, guys. Your exponent becomes your coefficient, and divide both sides by log 6. Bingo. Now I can stick that into my calculator pretty quickly. And again, we get an approximate value of this 1.39er. I really don't like this idea that we're approximating these things. I got to tell you that. Well, more about that later on. Okay, let's keep going. All right. So all I can really do at this point, like you know everything at this point, honestly, about solving these. The last little piece here is just, I'm going to throw in some coefficients and see what happens. Okay, first thing, amigos, you cannot multiply a coefficient and a base together. For the love of Buddha, do not tell me that is that. That is so no bueno, it's not even funny. Don't do that. Let's try it again. Well, if I can't multiply it, maybe I should divide it. There we go. Can't make the bases the same, turn it into a logarithm. Take the log of both sides, like that. Exponent becomes my coefficient. And I'm going to put that x plus 1 like that in brackets when I bring it down, parentheses I should say. Now I'm going to divide both sides by x log 4. And to finish this off, subtract 1. And there it is. I'm not even going to bother to put that in my calculator to see what that value is for now. Okay, so if there's a coefficient, what did we just learn? If there's a coefficient, let's get rid of it by dividing. All right, let's try a couple more. Next one, again, I can't multiply the 2 and the 3 together. So now I'm going to divide both sides by 2. Which is 6. Can't make bases the same, so now I'm going to turn it into a logarithm by taking the log of both sides. Power becomes a coefficient. Divide both sides by that log 3 right there. And now, to undo the division, the inverse of division is multiplication. So I'm going to multiply both sides by 4. Just like that. Again, I don't even want to put that in my calculator, because when I put this in my calculator, I'm going to have to approximate it. I would prefer not to. That's a better answer, the way that's written right there. Okay, last one, F. Let's go for pretty orange. So I'm going to divide both sides by 10. I think you've got that figured out by now, right? That's 12. I say to myself, can I make the bases the same? Sir, no, sir. Take the log of both sides. So do you see how I'm always trying to make, or I'm at least asking myself, can I make the bases the same first? Now I'm going to make that power into a coefficient. If you want, maybe you could even write that 1/2 as 0.5. There's nothing wrong with that, really. And I'm going to divide and multiply here in the same step, because I think we're getting the hang of this now. There it is. Again, there's my exact value answer. Love it. Okay, so logarithm's not so bad. I hope that's what you're thinking. You're like, hey, this isn't bad. I got this. I still don't know what a log is, what my calculator is doing when I punch that button, but that's okay. Now, this is really important. There's one more step that we could use to simplify our previous answers. We can actually write all of our previous answers as a single logarithm called change of base. This right here. So right now, here's where we're at. Our answers look like this. What I want to do right now is teach you our last law of logs. I want to write it like this. Okay, let's go check this out. It's actually really easy. So let's go back to maybe just A and B. You'll see how quick this is. So again, where we were at here, our answer for this one was log 81 over log 10. So change of base tells me this. It says I can simplify this into one log. It goes like this. What's in my numerator, the 81, is inside my logarithm. That's known as the argument. And the bottom argument in the denominator becomes the base. Guess what? If you put both these things in your calculator, you get the same answer. So this is just an extra step to simplify at the end. Okay, the next one. Again, our answer for this one was this. So we could simplify this using change of base. What's in the numerator stays my argument. What's in the denominator becomes my base, just like that. Now, most calculators can only handle base 10. We'll talk about that in a calculator video to help you out. Okay, this last one here then, I'm hoping you can tell me that this would be, I like it. Okay, so we've got an extra step to simplify. Now, usually at this point, someone in the class of 35 shouts out and says, oh, I just noticed something. Look at this. Do you notice a pattern going from here to here? Look at this. There's a shortcut that we can take. And I'm fine with the shortcut if you notice it. Look at that. Base of 10, base of 10. And the 81 and the y switch spots. Now the y is by itself and the 81 goes with the 10. Let's look at the next one. Base 5, base 5. The y is now by itself and the 8.32 switches and goes with the 5. Base is 6, base is 6. So I should have written an x there, not a y. I don't know why I wrote a y. The x goes by itself, and the 12 goes with the 6. Okay, this is a shortcut that we can take. Right here. There's an important shortcut that we could go to right to our answer. This is our last law of logs, and this is on the formula sheet. My little expression is the base stays the same and the other two parts switch. They're switching because it's an inverse. So what this is going to become is base stays the same. So I say right now my base is b, and the other two parts switch. So the y goes where the x was, and the x is solved for. How handy is that? So let's practice this a few times. So here, again, we've already done these ones, but let's do it again. So base stays the same, so log base 10, the other two parts switch. Base stays the same, the other two parts switch. Base stays the same, the other two parts switch. How cool is that? All right, we're almost there. We're almost at the end of this lesson. What do we do if we're working with a log equation instead of an exponential equation? Well, what I'm going to say to myself is my unknowns inside my logarithm. So guess what? I'm going to turn it into an exponential. They're inverses of each other. So my expression stays the same. Base stays the same, so base of 5, the other two parts switch. So now the 3 becomes the exponent, and there's x. So x is 125. My unknowns inside my logarithm, I'm going to turn it into an exponential. Base stays the same, the other two parts switch. And now I'm just going to divide both sides by 3, and guess what? That's 27. Okay, last one. Unknowns inside my logarithm, I'm going to turn it into an exponential. So I'm going to divide both sides by 3. Unknowns in my logarithm, I turn it into an exponential. There it is. And you could go ahead and stick that thing in your calculator. It's going to give you the cube root of 16, whatever that is. There it is. So not only does the laws of logs help us solve exponentials, they actually also help us solve logarithmic equations. Cool stuff. Okay, let's wrap this up and we are done. Exponential functions and logarithmic functions are inverses of each other, meaning they undo each other, like adding and subtracting, multiplying and dividing, exponentials and logarithms. If we have an unknown exponent and cannot make the bases the same, we must use logs, or we could graph and cheat. To switch between exponential form and logarithmic form, my little expression is we keep the bases the same and switch the other two. Or look on the formula sheet. Our calculator uses base 10. To change base, we must use change of base formula. Unless your calculator has a fancy log button, which some of them do. You can never take the log of a negative number. Your calculator will return an error. And this is a bit of a preview for a future lesson. I need you to know that log base a of a is 1. Because log base a of a, using change of base, is a over a, which is 1. Okay, that'll be important for next lesson. Okay, last little thing I just want to show you here, just in case, and then we'll stop. So the first one says convert to a logarithm. Okay, no problem. Base stays the same, the other two parts switch. So that's us taking the shortcut because we can. Now, if I don't have my fancy log button, you're going to have to use change of base, and you'll put it in your calculator like that. What we just did there was we just made that base immediately 10 by doing that. Okay, that's it, friends. Hope that worked for you. Have some fun solving some equations. Never forget, you can always graph and cheat. And if you're not cheating, you're not trying hard enough. Okay, See you next time.